Imagine you're an astronaut floating in space, and you accidentally get too close to a black hole. What happens next? Do you get crushed instantly? Do you burn up? Or maybe you get frozen in time forever? The truth is far stranger than any science fiction movie has ever shown you. Black holes don't just kill you, they mess with the very fabric of reality itself. Time slows down, space stretches, and you experience things that would make even the wildest Hollywood special effects look boring. Today we're taking the ultimate journey, a one-way trip into one of the universe's most mysterious and terrifying objects. We're going to follow you step by step as you fall toward the event horizon and beyond, using real physics to understand exactly what you'd experience. And here's the mind-bending part. Depending on who's watching, you might die in completely different ways, at completely different times. So buckle up, because we're about to dive into the most extreme physics in the universe. Before we send you on your cosmic death spiral, let's understand what you're actually falling into. A black hole is what happens when matter gets compressed so densely that its gravity becomes so strong that nothing, not even light, can escape. Once it crosses a boundary called the event horizon. For our journey, let's say you're approaching a black hole 10 times the mass of our sun. The event horizon would be about 18 miles across, but the actual matter creating all this gravity is crushed down to a point with zero size but infinite density, what physicists call a singularity. Now you're starting your fall from about 1,000 miles away. The first weird thing you notice is what happens when you look at your friend who's staying behind at a safe distance, watching through a telescope. To your friend, you appear to be moving normally at first. But as you get closer to the black hole, something bizarre happens. You start moving slower and slower from their perspective. This isn't because you're slowing down, it's because time itself is slowing down for you relative to your friend. This is called gravitational time dilation. But from your perspective, everything feels completely normal. Your watch ticks at the same rate. It's only when you look back at your friend that you notice their clock's running faster and faster. As you get closer, the black hole doesn't look like a black sphere. Its intense gravity bends light around it, creating distorted images of stars and a bright ring of bent starlight. At about 50 miles away, you start feeling the tidal forces. Gravity at your feet is stronger than at your head because your feet are closer to the black hole. You start to feel stretched. Now we get to the part movies love to dramatize, spaghettification. As you fall toward the black hole, the tidal forces get stronger and stronger. Remember, gravity follows an inverse square law. Halve the distance, and gravity becomes 4 times stronger. At about 20 miles from the event horizon, this becomes seriously uncomfortable. Your feet experience significantly stronger gravity than your head, so you start getting stretched vertically while being squeezed horizontally. You're literally being turned into cosmic spaghetti. The size of the black hole matters here. If this were a smaller black hole, spaghettification would kill you before you reach the event horizon. But our bigger black hole means you might actually survive long enough to cross the point of no return. And now we reach the most mysterious part, crossing the event horizon. Here's what blows most people's minds. Crossing the event horizon doesn't feel like crossing a boundary at all. There's no wall, no barrier, no sudden change. You wouldn't even know you'd crossed it. Think of it like going over a waterfall in a canoe. Once you go over the edge, no amount of paddling can save you. The event horizon is like that edge, except you're fighting against the current of space itself. Once you cross, all paths lead toward the center. It's not just that you can't escape, the very geometry of space is warped so that every direction points toward the singularity. From the outside universe's perspective, you never actually cross. You appear frozen there forever. But from your perspective, you cross it and continue falling inward normally. If you look back toward where you came from, you might see the entire future history of the universe flash by in moments. Light from outside gets compressed and blue shifted. You might see stars being born and dying, galaxies colliding, maybe even the heat death of the universe all in your final moments. Now we need to talk about one of the most controversial topics in modern physics, what actually happens at the event horizon when you combine quantum mechanics with black holes. For decades, physicists thought you'd cross the event horizon smoothly. But in 2012, physicists discovered a major problem. If black holes obey quantum mechanics, which they should, then the event horizon might not be the smooth boundary we thought. Here's the issue. Quantum mechanics says information can't be destroyed. But if you fall into a black hole and get destroyed, What happens to all the information that made up your body? The math suggests that to preserve quantum information, the event horizon might actually be a wall of extremely high-energy particles, a literal firewall that would incinerate you the moment you try to cross it. So which is it? Do you pass smoothly through the event horizon, or do you hit a wall of fire that destroys you instantly? The honest answer is that we don't know. This is one of the biggest unsolved problems in physics right now. Some physicists think the firewall only exists for very old black holes. Others think it exists for all black holes. Still others think there's no firewall at all. Different theories predict different outcomes, and we have no way to test them because nobody can come back to tell us what they experienced. Let's assume you somehow make it past the event horizon. What's waiting at the center breaks our understanding of physics entirely. The singularity, a point where all the black hole's mass is crushed to zero volume, creating infinite density and infinite gravity. When physics deals with infinities, it's usually a sign our theories are breaking down. Before you reach it, tidal forces become absolutely extreme. If spaghettification didn't get you at the event horizon, it will definitely get you here. You're ripped apart at the atomic level. First your body, then your organs, then your cells, then your molecules, then even your atoms. But even this might be wrong because we're using classical physics where it doesn't apply. Some theories suggest quantum effects prevent collapse to zero volume. Maybe the singularity is a portal to another universe. Maybe time itself ends there. The singularity represents the limit of human knowledge. Now here's something that might blow your mind even more. Black holes aren't actually black, and they don't last forever. Stephen Hawking discovered that black holes emit radiation and slowly evaporate. This seems impossible since nothing escapes black holes, right? But Hawking radiation comes from the event horizon itself. Quantum particle pairs constantly pop into existence in empty space. Near the event horizon, sometimes one particle falls in while the other escapes. The escaping particle becomes real radiation, while the one falling in reduces the black hole's mass. Over time, this causes the black hole to evaporate. Our sun-mass black hole would take longer than the universe's age to evaporate completely. But smaller black holes evaporate faster and get hotter as they shrink. In the far future, they'll be the hottest objects in a cold, dark universe. This creates another mystery. If black holes evaporate completely, what happens to all the information that fell into them? This is still one of physics' biggest unsolved problems. Let's see what your journey looks like to your friend watching from safety. From their perspective, your fall starts normally, but as you approach the event horizon, you slow down more and more while your light shifts redder and redder. From your friend's perspective, you never actually cross the event horizon. You appear to freeze there, slowly fading from view as your light gets stretched beyond detection. To them, you spend eternity at the event horizon. This creates the black hole information paradox. You never cross from the outside perspective, but you definitely cross from your own perspective. Both are real according to Einstein's relativity. There's no universal timeline everyone agrees on. So what really happens if you fall into a black hole? The honest answer is we still don't know for sure. From your perspective, you might pass smoothly through the event horizon until tidal forces destroy you, or you might hit a firewall that incinerates you instantly. From outside, you never fall in at all. Both perspectives might be correct. Black holes exist where our two best physics theories, general relativity and quantum mechanics, contradict each other. These contradictions become impossible to ignore near black holes. What we do know is that black holes are far stranger than science fiction imagined. They're places where time slows down, space curves back on itself, and normal cause and effect breaks down. They're cosmic laboratories testing the most extreme physics possible. Maybe that's the most remarkable thing. They remind us how much we don't understand about our universe. Every time we think we have them figured out, they reveal new mysteries that challenge our basic understanding of reality. Black holes aren't just cosmic monsters, they're windows into the deepest mysteries of existence itself. In a universe full of black holes, we're all just temporary arrangements of atoms trying to understand the incomprehensible. What do you think happens when you cross the event horizon? Team firewall or smooth crossing? Let me know in the comments. And if this journey into extreme physics blew your mind, hit that like button and subscribe for more cosmic mysteries. Thanks for taking this journey with me, and see